All right. So continuing from the last class where we did up to Menger's theorem in connectivity, we'll continue on a related topic, but actually a very important one today. That is on directed graphs, and we'll learn about network flow and then end with max flow mean cut theorem. Okay, so far we have been mostly dealing with undirected graphs, and now we will consider directed graphs, but not just directed graphs, a little bit more than that. So a network uh, consists of, first of all, a directed graph, which is the base of it, underlying directed graph. Okay, we also call it digraph, and with usual vertices and edges. But for a network, what we further need is a source and a sink. That means a source from which something flows, and the sink into which the flow goes in and vanishes. All right, you can think of it as a water flow or something like that, right? So water flowing, lots of pipes and stuff like that, and water, there is a water source, and then there is a sink where all the water goes. A capacity function from V cross V to non-negative real numbers. So V cross V to non-negative real numbers means for any two vertices, there is a capacity. And the capacity is at least 0, but can be more than that. So that means the capacity of the flow, of whatever can flow from any vertex to any other vertex. Now, obviously, we are starting with the assumption that we have an underlying graph, directed graph, and you already know what a directed graph is, right? It's just that the edges have some direction. Now, but not all of the vertices, not between any two vertices we may have an edge. It's possible that two vertices are not connected by an edge. So then the capacity is just 0. So if there is an edge, then we would expect that that edge has positive capacity. And if there is no edge, then essentially the capacity is 0 anyway. So that's why it is okay to define it like this, that it's a function from V cross V to R greater than or equal to 0, non-negative reals, with the capacity being 0 if that's not an edge. Now, in this context, whenever we say UV, we mean the directed edge UV. That means U to V, not V to U. So here, V to U and U to V will be considered different. Okay. And in other words, capacity is there only for existing edges. So this is a picture of a network. So here we say this is a source, this is a sink. Okay. In this picture, obviously, we have drawn it in the following way, that from the source, flow only goes outwards. So it flows from the source and it only goes into the sink. So there is no edge from any other vertex into the source, or no edge from the sink to some other vertex. But we'll see later on that certain properties, after we prove certain properties, we'll see that that is we can actually construct networks without this, but then we'll have to set the capacity appropriately in. So essentially, source is really intuitively it's just a source. It provides the flow, and sink is what it takes in everything. So these are the capacities in my picture. That means the capacity of this edge is 5, this edge is 4, but only in this direction. Okay. So in this picture, none of the edges are bidirectional. That means it is just for an example. It is always possible that you have an edge like this also. For example, you may also have something like this. So, oh, sorry, both way is also possible. But just for the sake of clear understanding to start with, we are just taking a network which looks good. All right. So now what is a flow? We are already talking about from the source to seeing things flowing, but we need to mathematically and rigorously define what we mean by a flow. So to do that, firstly, for any set of vertices A, okay, okay, this is actually should not really be subset equal to, it should be a strict subset. Just think of this as a strict subset A subset of B. A bar with this square bracket, we will actually define, give it a nicer name later on, but just hold on for some time for that. So this A bar will be the set of all edges from A to the complement of A, right? So UV in the set of edges such that U belongs to A and V does not belong to A. Again, these edges are directed edges. So that means all edges from A to V minus A. So let's say if this is my A, I have marked them by red. Okay, if this is my A, set of vertices A, and then these are the set of edges A bar. Hopefully I have done it right. So it should not be from A to A. So this edge will not be a part of it, right? This edge will not be a part of it because although the U is in A, V is also in A. So that's not what we want. What we want is U is in A, V is outside A. U is in A, V is outside A. U is in A, V is outside A. Right. So basically, all edges from A to the complement of A. So that's A. That's this thing. Okay. So A bar. Now for any function, of course, we have already seen the capacity function, right? So this was the capacity function. But let's think about some other function. So any other function, V cross V two real numbers. So any other function for any pair of vertices. Let's define F plus A to be the sum of Fe, where E belongs to A bar. So what it actually means is, here, for example, this is our A, right? So this is our A, and similarly F minus A will be E belongs to A bar A. So what are the edges A bar? They are from A to A bar. So essentially, for whatever this function is, you can, for example, think about the capacity function itself. Okay, then it would be the sum of the capacities from A to A bar, from A to elsewhere. And similarly, F minus A is from elsewhere to A. So let's do it in this example here. Okay, let me actually, yeah, so let's do. So let's take the capacity function. So alpha plus A is the sum of the capacity of all these red edges, right? Right. So sum of the alpha for all these red marked edges. Is that clear? Now you tell me what would be alpha minus A. So which ones will be included? This edge will be included, right? Because this is from elsewhere to A. So 5. Will this edge be included?
No. No.
This edge will not be included. What about this one?
This will be included.
This will be included. So 5 plus 6, 11. Any other edge?
No, sir.
What about
that
this?
4.
That 4.
Yeah. So that another one. So I think it's 15, right? So 5 plus 6 plus 4. All right. So this is for alpha. Similarly, for any other function also, we may have the same thing. If we define any kind of a function on each edge, we can define that function plus and that function minus for a subset of vertices. Clear? At this point, it might look a bit abstract. Why are we defining such strange notations? But it will be, we'll give it, pretty good meanings very soon. So now, similarly, just like you can define these notations F plus, F minus for vertices, so set of vertices, you can also do it for single vertices. I mean, single vertices is just considering a single vertex u as the set of vertices, right? So, if we just think about this particular vertex. So, for this particular vertex, alpha plus of this vertex will be actually 5 plus 4, right? 9. Only these two are going out of this vertex. Okay. And then the in will be 5 and 4, 9. In also in this case is 9. It's not necessary, by the way, that for this any function that both are same. For example, you can look at this vertex. So here the alpha minus is 4 and alpha plus is 7, right? So, now I think you are starting to realize that what we are doing essentially for the capacity function, the plus and minus denote the incoming and outgoing capacity, right? So the incoming is minus, the outgoing is plus, right? So for example, if you take this vertex, it means the incoming capacity is 4, outgoing capacity is 7, right? Okay. So we can define this plus and minus for set of vertices or single vertices. All right. Now we are ready to define a flow. A flow in a network is a function like this. Okay, we are calling it f because we will keep calling f flow f, right? So it's a function, but just not any function. Okay, it's just not any function. It has certain conditions. That flow through an edge is at most the capacity of the edge. So the flow is tied to, first of all, your network has a capacity, right? So a flow can be on a network, but you obviously, if the capacity of this edge is 5, you cannot let more than 5 flow through this edge, right? So the flow through an edge is at most the capacity of the edge, which means, of course, the flow is non-negative, but it's also at most the capacity of the edge. And for every vertex other than the source and the sink, the inflow is equal to the outflow. So inflow is equal to outflow. That means f plus u should be equal to f minus u for all u that is not the source or not the sink. All right. Okay. So now tell me, the capacity function that we have here, is it a flow? I mean, is it good for a flow function?
No, sir. F plus and F minus are not equal.
Right. So there are quite a few vertices for which f plus and f minus are not equal, right? Well, there are quite a few for which they are equal as well. I mean, for example, for this one, we figured, yeah, they are equal. But there are other vertices for which they are not equal. So this capacity is kind of what is the maximum for each edge, but the flow is then whatever comes in also goes out. So you cannot store anything. None of the nodes can store anything. So this gives you a couple of intuitions. For example, you can think of a road network, right? So you can think of a road network without any garage anywhere, that whatever comes in, all these junctions, the vehicles must also go, so they cannot stay there. So whatever comes in must go. Or you can also think about like water pipe and stuff like that, right? So where everything that flows in must get out. Okay, so here let's try to construct a flow if I have not made any mistakes. So let's say I give this flow 4 and I give this flow 5. Now this 4 must get out of this, and I give this 3. So 5 comes in, 3 goes out, but maybe something more may come in here. But 3 and 4 goes into this. So 7 goes into this. So I must have 7 going out here. So I have done something. Also here I made 1 here. Actually, I did something and then manually adjusted, hopefully to make it correct. So here 4 full capacity, and then so here 4, that means this has to be 3, right? So 4 plus 3, 7 goes in here. So 4, if this is 4, this has to be 3, and if this is 3, and okay, so if this is 3, 1 goes out, the rest 2 must go out here, right? So they are determined now, and now 4 comes in here, so they must be distributed. So maybe I put a 0 here and I give a 4 here. So then 0 goes in, 3 comes, 1 goes, 2 goes. So that's all fine. I think the whole thing is now fine. Of course, source and sink, the in and out are more than that, 11, right? So, oops, sorry, there is some mistake.
Sir,
No, there is some mistake somewhere.
in
Okay,
the bottommost vertex, incoming is 6, but outgoing is 7.
that is why, because yeah, right, this one is not correct, right? In the bottommost, incoming is this one.
5 plus 1 and outgoing is 4 plus 3.
Yeah, right. So let's make it 3 then. If we make it 3, we'll make it 3, then this will be fine, right? Let me just do that, just a moment. Because these slides are required for a lot of things. I'll just, yeah, exactly. So if we make these two like this.
Sir, why are we not keeping that 6? Why are we making it as 5?
Just a moment, I'll just come back to you. Let me, let me just correct these numbers. Okay, I think, yeah, I think only for a couple of slides we need this. We will come back to this later. So, yeah, what is your question now?
Sir, that bottom edge, that was 6. Why are we making it as 5?
This one?
Yes.
Okay, no, I just gave it some flow. Now, if we make it 6, and then let's say if we make this one 6 and this one 4, right? So we'll have 10 incoming, but we can only have 8 outgoing.
Okay.
And then there is also another, yeah. So there are constraints. So there are also reasons why I did not give this flow full capacity. Okay, so now I think this is good as a flow, but let's move on. So this is a valid flow. Now, obviously, as you asked, your main concern was, well, we have more capacity, but why are we not letting that much flow, right? So, well, I mean, let's say there is less traffic right now, so we'll see. That is where the max flow and all those things will come in, right? So let's just wait for some time. So this is a flow function in this picture. All right. Now, resultant flow and max flow. What are the definitions? So this is the same flow function I have copied from the previous slide. I also corrected the 3's here. So here, let's say this is our set of vertices. This is the flow function. This is our set of vertices. And with respect to those set of vertices, we want to do something. So for a flow and a subset of vertices, again, I mean, make it a strict subset, doesn't really matter. The value of the flow is defined as, so value of the flow is defined as val fa. So the notation is like this: value of the flow f val of fa is the outgoing minus the incoming. Okay, so the outgoing from A minus the incoming to A. Now this is for a subset of vertices. It's also called the resultant flow from A. Now obviously what it means is that, I mean, how much extra is getting out, right? So how much extra is getting out from A. So in this case, if this is our A, right? So these two, what is the value of FA? Well, here for the total incoming is 4 plus 3. Oh no, sorry. So sorry, 3 doesn't count because, so total incoming is 4 and 5 here, right? So 9. 3 is within A. So 4 and 5 comes in, also 1 also comes in from outside. So 10 is total incoming, and outgoing is 3, 4 and 3. So again 10 outgoing. So the val is actually 0 for this subset A, right? So these two vertices. Now the value of the flow function, overall flow function, okay, the value of the overall flow function is denoted as val f, and that is essentially nothing but the value of the source. How much is getting out of the source? So value of the flow is essentially how much is getting out of the source, right? And in this case, what is it? Flow out of the source is 10, right? So 6, oh sorry, okay, let me see, should be 9. Let me just quickly do that as well. I think what I did was I initially gave some numbers, and later on when I changed certain things, some mistakes happened anyway. And that's a good thing that we are going through it. Yeah. Okay, so in this case, the value of the whole flow or value of the source is 9, 4 plus 5. Now, what is a maximum flow? A maximum flow is a flow such that there is no other flow with more value. Well, that's obvious. Here, what we are essentially doing is we are letting 9 units of whatever flow out of the source, and 9 units are getting into the sink, right? And you can intuitively already understand, we are going to actually show that also, but you can intuitively already understand that whatever comes out of the source has to get into the sink. Do you also see something more here? This thing, value of this set A was 0. Is it necessary that it has to be 0? Okay, so let's see. So, but in other words, the main point here is in this particular flow, we have 9 getting out of the source and 9 getting into the sink, and that's the value of the flow. Is it a max flow? Well, we don't know really yet, but in case it is a max flow, then there should not be any other flow which has value more than this. Or in case if it is not a max flow, then there will be some other flow function which has value more than this. That means more than 9 has to get out of source and the same amount has to get into the sink. So the properties of flow and max flow and resultant flow are the following. Now, obviously, if A is a subset of the vertices except the source and sink, then its value has to be 0. Okay, and value of the flow is value of the source, defined as value of the source, and that has to be equal to minus of the value of the sink. All right, so I'll leave the proof for these two things for you to work it out yours, but intuitively they should be very clear, right? Did anyone have a question? Okay, fine. So let's move on. So the next concept is improvable path. So let F be a flow in a network, and let P, these are the edges, E1, E2, dot, 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 En, be an undirected path. Now, of course, we are considering a directed graph only, but in this case, we will just not think about the direction for just the path P. So let P be an undirected path in N. Well, this network in some books, N is the parent network, where they write it as G. It doesn't really matter as a matter of notation. I'm just writing NVE. So So let's say this is an undirected path. Okay, so let's see an undirected path is something like this. Okay, I think it's visible, although I decided to keep it below the flow numbers. Now, it is not necessary for the definition that the path has to be from the source to the sink, but I don't want to draw too many pictures. It takes me a lot of time to create this picture, so I don't want to draw too many of them. So, in this case, I have just drawn a path from source to the sink, but note that this path is really undirected. Like, this is along the direction of the edge that was there, but then the path went like this, and this was against the direction of the edge. Similarly, this was against the direction, this was against the direction, this was again along the direction. So we are really discarding the direction portion here, and which means that this path is actually just an abstract concept. Nobody is going to go through this path, right? So the network does not allow you to come from here to here, right? So the path, this path is not for practical purposes. This is just for us to prove certain things or define certain mathematical concepts. So yeah, so this is an undirected path. Then obviously, as I already explained to you, edges along P are the ones for which EI is VI plus 1. So one can want to be absolutely rigorous, one should define what is VI plus 1, but it's kind of clear from this that in the path, if there is an edge from the previous vertex to the next vertex, like this one, right? So from this vertex to this vertex, in the original graph, there is actually an edge like this in the same direction. So then this is an edge along P, right? So this edge is along the path, and the other edges are against the path, like this is against P, right? So this is against the path, this is against the path, this is against the path as well. Okay, and again, this is along the path. Now, definitions. Iota, okay, iota is like I of the Greek alphabet. Okay, so iota without the dot. Iota of an edge is defined as alpha minus f. Now, this all thing we are actually doing in the context of a flow and the network. So, if E is along P, then it is the capacity minus the flow. And it is just the flow if it is against P. So let's do that. And what we will do, there are two colors here. The red one is for the edges along the path, and the purple ones are against the path, just to make sure that we understand this. And in fact, this thing may actually look a bit counterintuitive to start with, but let's do that. So this portion is actually easy to understand. This is the capacity minus the flow. That means here the capacity was 5, the flow is 4. So what will be iota? This is along the edge. So iota will be, okay, sorry, iota will be 1 here, right? Iota will be 1 here. This 0 actually should not be there. It's not even on the path. So, forget this 0. So this iota is 1 here, because capacity is 5, but the flow is only 4. In other words, it is kind of, we are talking about improvable paths, and this is the I of Greek letter. So this iota stands for something to do with improvements. Okay. So essentially it means that we can improve this flow a little bit more here, and we can improve it by 1. Okay. Now, what would be the iota for this edge? What will it be for this edge?
2.
Yeah, it should be. Oh, sorry, I did this one first. So this one is also against the path. So this is 1. Okay, no, it should be 2. I'm sorry. This should be me just correct. I think those numbers, yeah, the 3 I need to correct back here. 3, 3, 2, and this should be 2. Yeah, now it looks fine. So play. Yeah, all right. Okay, the path will be drawn again. Yeah. So 1, 1, and 2. So this will be 2 because it is just the flow. Yeah, I corrected the 3 again here. All right, and this one should be 1 because it is just against it again, right? So it's just the flow, and this one will be 5 minus 3, right? Because the capacity is 5. This is along the path, so this one should be 2. And these red ones are the along the path. The purple ones are against the path. Now, okay, yeah. So these actually don't matter in this particular case. Forget about it. So the I for the iota for the whole path is the minimum of the iota values for all of the edges. So for this whole path, then IP is 1, right? So 1, 2, 1, 1, 2. Right? So 1 is actually the improvement, suggested improvement for this path. Now, yes.
Excuse me, sir, you are telling that path is affected. So how you are calculating against the path?
Right. So that is the counterintuitive portion, right? So this one, how we are right. So that is your point. Now, okay. See, the point is, yeah. So the point is the following. You that whatever flow you have defined is okay, but there is an iota of p path. Now, that means can send 1 unit of flow more along this path. Okay, I can send 1 unit of flow more along this path. Now, your problem is, well, I cannot send anything along this, right? Because I don't have an edge along this. Well, nevertheless, I can reduce this, right? I can reduce the flow from this to this, and that I can reduce by up to 2. So the against portion, how much can I improve at most? I can improve at most by whatever is flowing. That means there may be some flow which is actually against my goal. So along this path, I can improve the flow by 1. And how can I do it? I can make this 4 into 5. I mean, I can make 4 to 5. I can make this 2 to 0. I mean, or maybe to 1. I can make this 1 to 0, this 1 to 0, and I can make this 3 to 5. Now, obviously, at this point, this path may not actually be the only hope to improve my overall flow. There are other ways the overall flow can improve, right? But basically, what happens, I'll tell you. Sometimes there can also be bidirectional edges. You can go from here to here as well as here to here. Now, what might happen is you are sending 4 along this direction and 2 along that direction. You're essentially, just traffic is going round like this. Instead, if you decrease this portion, then that may actually improve the overall flow. So the intuition behind the against portion is, if your goal is to go through this path, the against flow is actually disturbing you, or going into the opposite direction. So you can decrease it, and decreasing this would mean the flow along this is increasing. Now, obviously, that's an abstract concept, because in this particular example, you don't actually have a path from here to here at all. But in case you had, decreasing this direction would help you to increase the other direction. So that's the concept. So let's move a little bit forward. And then a path P from the source to the sink is called F improvable if iota of P is positive. So in this case, obviously, this path is F improvable. Okay, this path is F improvable because IP is positive. Now, in other words, what it would tell you is something, if you change the flow along this path, you would probably improve. That's what it tells you. Okay, so this path is an example of F improvable path. Now let's see what is the relationship between max flow and improvable paths. Now from here on, things might get slightly abstract. It may not be very clear for you to see exactly what's happening. So sometimes you may have to just depend on the mathematical derivation, but let's see how it goes. So in a network, if F is a maximum flow, it's actually a theorem, then it has no improvable paths. Folks, actually, I have not written in the form of theorem and corollary and stuff like that. In the books, they have it that way, but they're just following one from another. So this is actually one of the theorems that if F is a maximum flow, then it has no improvable path. Well, then what we already worked out tells us that the flow that I have assigned is not a maximum flow. We could do better. Okay, and that's why the terminology improvable comes in. So let's prove this. So let us consider, we already have this flow F, right? Let's consider F prime as F prime E for every edge would be the flow F plus basically, basically here what we are doing is we are assuming if there is any improvable. Basically here what we are doing is we are assuming. I couldn't hear you. Can you repeat? Priyabrata, can you repeat? I couldn't hear you.
Hello.
Yes, tell me.
Sir, your voice was breaking. Maybe I think it is my network issue. Maybe.
Oh, is it? Can everybody else hear me?
Maybe the last part I missed a bit.
Which part? This one?
Last 1 minute. What you said.
Okay. No, it's just what we are doing is we are just trying to prove that in a network, if F is a maximum flow, then it has no improvable path. Now, suppose there is some improvable path in spite of F being a maximum flow. Okay, then let's construct F prime as for every edge Fe plus the improvement that I can make if that edge is along the path, Fe minus the improvement I can make if that edge is against the path, and let's not do anything for other edges. So for example, for this one, okay, so for this one, the modified flow, this one should be, I already have flow 4, the improvement is 1, so my flow will be 5, right? F prime will be 5. For this one, I already have flow 2. Oh, again, this 3 should have been a 2 here, I'm sorry. Yeah, let me just correct it because this 3 should have been a 2 here. Delete these unnecessary things. Yeah, okay. So yeah, we're back. Okay, so the modified flow here would be 5. What about this one? The next one? Next one, the flow is 2, but it is against the path, and my IP. Oh, no, sorry, just a moment. It's quite complicated at times exactly what is happening. So, all right. Yeah. So this is 5, and this one, the flow is already 2, but as we mentioned, the intuition is, well, if you want to do better on this path, then reduce the flow here. That's not helping, right? So what we do is we'll decrease it by the whole improvability of the path. So the whole improvability of the path is 1, so we'll decrease it by 1. So the flow, modified flow here will be 1. What about this edge? This edge is also against it. So this edge, the flow will be 0, right? So I have not drawn it here, but this edge, it will be a 0. This will be a 0. What about this edge? This edge will also be a 0 because it's also against, and so this minus 1. And this edge, the improvement factor is 2, so we'll make it a 5. Right? So essentially, that's what our f prime is. Now, the point is, capacities of the edges.
One question.
Yes.
That the improvement factor is for the whole path, right? That is
Yes.
1. So this last stage should
Oh,
be
right.
4.
I'm sorry. It should be 4. Yeah, you're right. You're right. Yeah, this should be 4. Yes. I mean, that is also a small mix up that I made before. Anyway, yeah, this should be 4. Good. So now the capacities of the edges are not exceeded by the formula itself. Why? Because IP is just the capacity minus the flow. So if I'm adding the IP here, sorry, I of the edge, and IP is the minimum of the capacity, minimum of the improvements of all the edges. So here I'm not exceeding the capacity. Here I'm not exceeding the capacity because I'm actually subtracting something, and here I'm not changing anything. So since f was a flow within the capacity, f prime will also be within the capacity. Okay, that's fine. But there is another thing that we need to check. Now, another thing is, for all vertices other than the source and sink, for f prime, the new values, is it true that the incoming is equal to the outgoing? Okay. So if that is true, then f prime will also be another flow, right? So let's check that. So if V lies between two edges along P, so for example, in this case, I think lies between two edges along P. In this case, we don't have one of this, but suppose the path is like that. Suppose the path is such that both edges are this directional and your path is also this directional. Okay. So if V lies between two edges, this is the vertex V. This is the vertex V. If it is between two edges along P, or both are against P, then it is obvious because nothing is changing, right? So then it is obvious because we are adding or subtracting IP in both cases to both the edges, right? Now the question is, if V is like this vertex, in this path, it is one edge along P and the next edge is against P. So if V lies between one edge along P and one against P, or the opposite, it will be similar. Then along P, we are increasing by IP and iota of P, and against P, we are decreasing by iota of P. So we are actually keeping the incoming and outgoing of V the same, right? So essentially what is happening is our f prime is also that also satisfies all the conditions of being a flow. The two conditions are being within the capacity and incoming equal to outgoing other than the source and the sink. Okay, so then what happens is the total value of f prime increases exactly by iota of p, right? So the total value of f prime increases exactly by iota of p, because from the source, that's what is happening, right? And then since iota of p is greater than 0, we can improve the flow, and f is not a max flow. So what we have proved is, if f is a max flow, then it cannot have any improvable path. By the way, by definition, improvable path is always source to sink, right? So by definition, improvable path we meant to be source to sink. So essentially, if f is a max flow and it still has an improvable path, then you can simply change the flow along the improvable path by the improvement factor or whatever of that path, and you can increase the total flow by that amount. And so since f is a max flow, you should not be able to do that. So it does not have any improvable path. Clear? Okay. So let's move on to the next. Well, we have talked about max flow mean cut. So what is a cut? So for a network N, let S, yeah, now by the time I came to this slide, I realized I should have used strict subset. Anyway, so let S be a subset of the vertices such that the source is a part of that subset, but the sink is not. Okay. So you are essentially taking a set of vertices containing the source, but not the sink. Then the cut by S is defined by the set of edges from S to outside. So I told you that I will give this a nicer name. Obviously, there we defined it for any subset of vertices, but for cut, we need this condition that it contains the source and not the sink. So this is essentially the edges, set of edges from S to S bar. S bar is, let's say, complement of S. Okay, so S to S bar. Okay, so here if the red vertices are my set of vertices S, and it contains the source and does not contain the sink, then my cut is the set of edges which is this one, but not this one, right? Not this one, because it is from S to S itself. Yeah, so not this one because this is incoming, not this one because this is also S to S itself. So this one, and then this one, but not this one, right? So I think I have made it right. So these are the edges which is defining the cut. So cut is essentially a set of edges. Now capacity of a cut is nothing but the sum of the capacities of the cut edges. All right, so capacity of the cut is the sum of the capacity of the cut edges. In this case, yeah, in this case, what is the capacity? Let's just 6, 4, 5, 4. So that should be 9. So set of vertices S, the capacity of the cut defined by S is 19. And the minimum cut, yeah, that's a reasonable definition. The minimum cut, a minimum cut rather, doesn't have to be the minimum cut. A minimum cut is a cut for which there is no other cut with smaller capacity. Okay, so a cut with minimum capacity is called minimum cut or min cut. Clear?
Sir?
Yes.
Sir, could you please define the cut once again? Actually, I lost it.
That's fine. Sure. So let's go through this once again. Define. Okay. So take any subset of the vertices such that it contains the source but not the sink. All right. So here, for example, this red vertices can be one such set. one such subset, right? Because it contains the source, not the sink. Now, that set of vertices defines a cut. What is the cut? All edges from these vertices to not these vertices, to the complement of this set of vertices. So that means here I have two kinds of vertices. S, those are the red vertices, and the white, those are the white vertices. So whites are the S bar. So all edges from red to white will be my cut. Or in other words, all edges from S to S bar. UV in the set of edges so that U is in S, V is not in S.
Hello, sir.
Yes.
Sir, why we haven't picked this two rightmost edge as a cut also?
Oh, I'm sorry. We should have. Yes, we should have. That's true. Let me just correct it. Let me do it right now because otherwise we might forget. Yeah, you are right. Thank you. So, just point this out because yeah. So that's also in the cut. So a minimum cut is a cut for which there is no other cut with a smaller capacity. Okay, now we will connect the concepts of flows and the cuts. So for a flow and a cut, for a flow F and a cut S, now a cut, we by this according to this notation, we will actually always write it as square bracket S. What we have is the value of the flow. Remember, the value of the flow is the amount of the flow coming out of the source and going into the sink. So value of the flow is same as value of the set of vertices S. So like cut is actually a set of edges, but they are defined by a set of vertices, right? So the set of vertices S, the value of these vertices, which by definition we remember that it is in outgoing from this set of vertices minus incoming to that set of vertices. That is the resultant flow of those set of vertices, right? So this is what we have to prove, that for a flow and any cut, we must have the value of S is this, value of the flow is this. Let's do the proof. So first, let us define Si to be the set S minus the source. So let's just take the source out of the equation for now. So all the vertices of S except the source. So then obviously we already know that if a subset of vertices does not contain the source, then the value of that subset must be 0, right? Because the incoming must be equal to the outgoing for that subset of vertices. We have already seen it before. I mean, we have not proved it, but it was simple, so I left it. Well, so if we take the source out of S, then the value is 0. Now let's actually write the value of Fs. Now value of Fs, capital S, F capital S is value of F of source minus all the vertices from the source to Si, the basically the value of that, or the flow of that, plus all the vertices from Si to the source. So let's look at this a bit more carefully here. Yeah, maybe drawing a little bit will help. So here we had the source, and okay, so here we had the source, and let's say from the source we are actually going to some more vertices. And these are your S. Okay, this is your S. Now this is your small s. Okay, I don't know whether that looks like an S. Okay, this is your small s. Now we know that the value of this portion is 0 because it doesn't contain the source or the sink. Now, but what is the value of the total thing? The value of the total thing is outgoing minus incoming. Now, total outgoing minus incoming. Now, total outgoing, then we must have value of Fs. This one we must add. But then from the source, we contribute to a lot of incoming here, right? So that we should subtract. And from the other vertices, in case there is something to the source, okay, that we should add, right? So that's what we have for this portion.
Sir, which one is S1?
F1.
And that you have written val S1? Or,
Where is F1?
oh, SI maybe.
SI.
Okay, okay.
SI, is it?
Yes, yes, yes.
Where have I? Oh, this one.
Yes.
Yeah, so SI is this thing that we have defined. S minus the source. So
Okay.
this is for all vertices. Basically it's like this. These are SVs are all these edges. Okay, and VS typically you wouldn't have any, but but in case you have opposite edges also, sometimes you may define it that way, that you have opposite edges also, right? Okay, so this is this portion. So val of Fs is actually this is this portion and the incoming of this also, right? So the other side. So this is this portion and this one is simply the opposite. So here we do val of Fsi plus this minus this. So then what happens is these two cancel out, these two cancel out. What remains is val Fs. Oh, and also val Fsi is val Fsi is 0, right? So because Si is nothing, so what remains is val of Fs. So this is then val of Fs is essentially val of F small s. If S is defining a cut, that means S actually contains the source and yeah, if S contains the source, then the val of this is equal to the val of the source. Intuitively, what does it mean? The val of the source is nothing but how much of flow the source is generating. Now, if you take any subset of vertices containing the source, but not the sink, then the value of that subset also must be the same. So in other words, if we draw this thing again, let's say I want to draw it. So this is a source, and I take another subset of vertices which is bigger than this. So this is my capital S, this is my small s, and my sink is here. Okay, so sink is here. So the amount of flow I am generating out of this is same as the amount of flow I am generating out of this. But intuitively, that is kind of clear because what is remaining in the graph? What is remaining in the graph is the other portion. This portion is remaining in the graph. And essentially, from this portion to the other portion, that much has to go. And they finally all have to sink in to R. Right? So outgoing of capital S has to be the incoming of R or incoming of essentially the S bar. Right? So that's what intuitively this result means. Okay, now let's continue some more with flows and cuts. So for a flow and a cut, we have to prove this. For a flow and a cut, is the value of the flow, that means amount outgoing from the source, is less than equal to the capacity of the cut. For any cut. By the way, remember that a cut has a particular property that this set of vertices contains the source. Okay, so what is the proof of this? By definition, we already know that f plus s, right? So f plus s is equal to, for all edges in the cut, the total flow, right? But the total flow has to be upper bounded by the capacity, right? So capacity of the cut. So it's clear that f plus s is less than equal to the capacity of s. Now, from this we have to get to value of f. Now, we have already shown that the value of f is the value of fs, and that is f plus s minus f minus s. So f plus s is already less than equal to the capacity, and the value is f plus s minus f minus s. So we are actually subtracting something here, and f is always, this is never negative, right? So it's never negative. So since it is always non-negative, we have value of f is less than equal to the capacity of the cut. Okay, good. Now, this is less than equal to, but can it ever be equal? Yes. In this, the equality holds if and only if, well, that's clear from this, obviously, because this is already less than equal to the capacity. Okay, and if this portion is positive, then this side cannot be equal to that side, right? Because this is already less than equal to. So if this is positive, then we cannot have it. So obviously, this equality holds if and only if f plus s is equal to the capacity and f minus s is actually 0. Okay, so that means overall to that cut, nothing is coming. Overall to these set of vertices, nothing is coming in, and whatever is going out is the capacity of the cut. That means it's going out in full capacity to the other portion of the graph. So this is possible. I mean, let's actually derive more from this. This is possible if and only if all edges in the cut have flow with full capacity, right? I mean, because of this inequality, right? So Fe has to be less than equal to alpha E. So if the equality only is possible, with each of them have to be the full capacity. Fe has to be equal to alpha E for all. Now, and then it has to be also the case that there should be no flow from S bar to S. S bar to S is this much, right? The flow amount of flow from S bar to S is this much. There should be no flow from S bar to S. And when can that happen? That can happen only if the opposite edges. So for example, let's say this is my S and this is my okay, so this is my S bar. Obviously, there can be some edges like this, right? There can be some edges with some capacity, but there should not be any flow along these edges. So Fe of 0, Fe has to be 0 for all E equal to Vu with V in S bar and U in S. Why so? Oh, so okay. So why so? Because if there is anything like that, then if there is any flow, then F bar S will actually be positive. Sorry, F minus S will actually be positive. So that means, okay, and it's a bold blue statement, which is kind of leading to the theorem that if value of the flow is same as the capacity of the cut, then F is a maximum flow and S is a minimum cut. Okay, now why so? Well, obviously, this is proven for any cut and any flow. So kind of the value of any flow is upper bounded by the capacity of any cut. So if it is equal, then f has to be maximum, because I cannot have anything else which is bigger, which has more flow, because then it will be then this theorem will be violated. Similarly, for this cut, I cannot have any other cut with lesser capacity, because then the capacity of that cut will be less than a flow, right? So essentially what it means is that if this equality holds, then f is a maximum flow and s is a minimum cut. But the famous theorem is not this. That is the converse of this actually. What we have shown here is, if the value of a flow is same as the capacity of a cut, then this is max flow and that is mean cut. What we want to show is the value of a max flow is same as the value of a mean cut. Okay. So, I mean, this does not necessarily tell you that this will always happen, right? So this may not even happen. That's the point. But yeah, what it tells you, that value of a max flow has to be same as the capacity of a mean cut. So let's go on to that. Okay, so let's prove that theorem. We'll actually prove a little bit of alternative statement, and which will essentially imply our theorem. A flow f of a network N is maximum if and only if there is no f improvable path in N. So a flow is maximum if and only if there is no improvable path in N. We have actually shown the one side of it. The if and only if, we have already shown one side of it before, right? We've already shown that a maximum flow does not have any improvable path. Now what we have to show, that if there is no improvable path, then this must be a max flow. So the converse is, assume that N has no improvable path, but f is not maximum. Now let again Si, I realize that this I thing is a bit difficult notation, but I believe, if you look at it carefully, Si is all set of all vertices. Okay, so let's just I know there is a lot of new concepts and new definitions and new terms. So remember, what is an improvable path? Improvable path is some kind of an undirected path like this, right? From source to sink, right? Such that the iota of that path is positive, right? Okay. Now we have already assumed that there is no improvable path from source to sink. Fine. Now let's just say from the source to set of all vertices such that there is some path with positive iota. So in other words, improvable path, but with a little bit of abuse of definition, not up to the sink, but maybe up to some other point. Okay, so maybe from the source to, some vertices I can still improve, but later on I should not be able to improve. That's what it means. So all vertices such that for some path from S to U, iota of P is greater than 0. Okay, and then define our S to be this Si and the source. Yeah, so this is the source. Now take some edge in this, and in the cut defined by S. That means from S, let me actually delete the annotation. That means from S, okay, maybe I'll draw it better here. So this is my S. It contains the source. And this is my, I changed the colors, okay. And this is my S bar. Okay. Okay, it contains the sink. Okay. So now let's take E to be an edge in the cut. That means a cut edge will be between them, right? So a cut edge will always be like this. From S to not S. So let E to be one such edge. Okay. That such that this portion U is in S and V is not in S. Now we'll claim that the flow across this has to be the capacity of that edge. That means the flow must be full capacity. Why? Because by assumption, there is a path from S to U with a positive improvement possibility. So by assumption, we know that from S to U, I have a path. Let's say this is my U. So this is my U. I have a path and I can improve this path. Okay. Now, this is my edge E. But since V is not in S, by construction, what is SI? By construction, SI is all paths such that I can improve. All paths up to certain vertices such that I can improve. But V is not in S. So in the extended path up to U and then this much, the iota must not be positive, because in that case, this vertex would have been a part of this set. If the iota of this is also positive, then this vertex would have been a part of this set. So the iota of this vertex must be 0. So this edge must be 0. So then iota of E must be 0. And then Fe has to be alpha of E. Okay. So if E is an edge like this, that the first endpoint is in S and the other endpoint is in S bar, then it has to be full capacity. Now let's prove the other side. If E is the opposite one, right? So that's possible that there are opposite edges also. Okay, that's possible that there are opposite edges also like this, right? From S bar to S. And there should not be any flow this way. So if E is it belongs to S bar to S, this set of edges, that means an edge from V outside S to U in S. Then if the flow from right to left here or S bar to S here on this edge is greater than 0, then for path PE, right? So then up to this much, again, up to this much, I already have an improvable path. Up to this much, I could already improve this path, right? Because that's how my S is constructed. And if this is also positive, I could decrease the flow there and improve the whole path, right? So if IPE, if this is positive, then we would be the minimum of this portion of the path and Fe, because against the edges against the path, my iota is just that much. Essentially, what it means is that I can decrease the flow. Well, there should not be anything to decrease here, and that is why. I mean, then in that case, obviously, iota of PE would have been positive, and then this vertex by construction would have been a part of it. So then V should have been a part of S by construction. Right? So that's a contradiction. So essentially, what it meant is then all of these edges must have flow exactly as much as the capacity, and then it means that there is no improvable path. oh, sorry, there is no improvable path, it also means that f is maximum, right? So hence, what we have shown is that the value of a maximum cut f is same as the capacity of a value of a maximum flow. Okay, I'm sorry, the value of a maximum flow f is same as the capacity. Okay, here are we. Yeah, the value of a maximum flow f is same as the capacity of a minimum cut. Okay. Now I can understand that is the proof clear to everybody, or if you have confusions, I would think that you should just go through again. Do you have any question immediately? Okay, fine. Then please go through and I will also share another material with you which you can read, but it is pretty much the slides are based on that. So I believe it will be same. Now let's look at another interesting connection. We looked at Menger's theorem in the last class, and we looked at the vertex variant. That means what we said is if it was a case of undirected graph, right? So in case of an undirected graph, if u and v are two vertices not adjacent already, then the number of vertices you need to make u and v disconnected is same as the number of vertex disjoint paths from u to v, right? So that was the Menger's theorem. Now that was a vertex variant, and there is similarly there is an edge variant of it. Okay, so the edge variant is disjoint version is let u and v be two non-adjacent vertices of a connected graph. Then the minimum number of edges whose removal would separate u and v equals the maximum number of edge disjoint paths from u to v. Now this is actually this is an easy consequence of the Max-Flow-Mean-Cut theorem, and the Max-Flow-Mean-Cut theorem is actually an extremely strong result which can prove a lot of other results in graph theory. So let's see how that can be obtained. So from an undirected graph, we can actually create a network by simply, all the undirected edges you replace by two directed edges, or for the convenience of drawing here, what I have done is I've just given the edges bidirectional. I mean, making them bidirectional. That means that there are edges in both directions. Now note that, however, there is a little bit of a problem that the capacity along both directions may not be the same. Okay, but for our purpose, I will not have a problem here. But in a typical network, the capacity this way and capacity this way, or capacity, let's say this way and capacity this way may not be the same. But in our case, we'll have all same capacity. So for this particular thing, this picture will suffice. But I just wanted you to understand that sometimes it is not enough to just draw it like this. You may have to actually draw two lines, one this way, another that way. Okay, so we set capacity of each edge to 1 in both directions. This way also 1, that way also 1. And setting u to be the source and v to be the sink. So whichever u and v you have, let u to be the source, v to be the sink. Then the maximum flow, note that although the capacity from some non-source vertex to a source is 1, it is not necessary that something needs to flow. Okay, it is not necessary that something needs to flow. In fact, it will be better it doesn't flow. Anyway, so then the maximum flow is equal to simply the maximum number of edge disjoint paths from u to v, because all of them are capacity 1, right? So whatever you make it flow, it's just the maximum number of edge disjoint paths from u to v, right? So that is the total flow, because they are never joining. The flows are never joining, right? And the capacity of a minimum cut is simply the number of edges across S and S prime, sorry, S and S bar, such that U is in one component and V is in another component. So essentially, the capacity of a minimum cut will essentially be the number of edges that you need to remove to make U and V disjoint. So essentially what we did was, from an undirected graph, we synthesized a directed graph, and we can derive Menger's theorem in a very easy way from the Max-Flow-Menkert theorem. All right, so that's it for today, and that's it for the Max-Flow-Menkert theorem as well. In fact, this there are a lot of other results that can be derived from Max-Flow-Menkert theorem. We will next go on to planarity of graphs, and I think it will take either we'll do planarity and a little bit of colorability in the next two classes, or we'll do planarity only and the colorability concepts will be introduced to you as part of exercises. Any question as of now? Please do one thing. I think a couple of the proofs in this class and the previous class towards the end was pretty involved, and you will need to read through them again. So if you have any doubts, please do ask. I realize that to the first 2/3 of the class, all of you, many of you were interacting a lot and picking up mistakes, and so that's how I understand that you are with me. But towards the end, maybe some of you might have lost it a bit, lost the flow of the proof, but that's okay. You just read it once more and you will get it. Okay then. So the next class will then be on Tuesday at 2 or 2:15 or 2:30. I'll post an announcement on the timing, but the next class will be on Tuesday at this slot. All right. Okay. Then I guess we'll end the meeting.